Okay, ladies and gentlemen, good morning, good afternoon. Not sure what time of the day you're watching this, but welcome to our first lesson of calculus, Intro to Calculus assignment number one, or notes number one, with assignment number one coming tonight or this afternoon. Before we dive into this note packet, what I need you to do is grab your calculator because decimals are super important in calculus. And if you open up your calculator or turn your calculator on or hit pause and get it, what we need to do is every time you do anything in this class, you need to hold three decimal places, not minimally, three decimal places every time. So when you turn on your calculator, what you want to do is you want to go to settings, number 5, and then you want to go to document settings. And in there, up here on display digits, you want to make sure you're on float. You don't want to be on float 1, 2, 3. You don't want to be on any of those. Or fix, you want to be all the way on plain old float. And make sure float is on. Radians and degrees are going to make a difference for us. Typically, we're going to be in radians. But calculation mode is auto. That'll give us exact answers coming out. We want to be real numbers. And if you weren't on float, make sure it's on float. Make that your default. And okay, that'll globally change everything. So I'm going to close that down now that we're in there for our calculator. And what we're going to be basically doing today is we're going to be using our calculator, refreshing your memory a little bit on some terms you probably haven't heard of since just about Algebra 2, but we're going to boogie through it. And what we're going to do is for the first couple we're going to use this first function right here, x cubed minus 2x squared minus 5x plus 6 is our example. Now what we're going to do on here is, the whole point is I'm going to graph this function in a second, and we're going to talk about different pieces and parts of the graph. First thing we want to look at is we want to look at x-intercepts. Remember, that is something comma 0. X-intercepts are exclusively when y equals 0 in our function, okay? When you're in a graphing page and you need to find your x-intercepts, you hit Menu, Analyze Graph, and you're looking for zeros. Sometimes I might say Menu 61. The 6 and the 1 are little hotkeys once you're in the menu to make it quicker, okay? The other thing we want to do is we want to recall ourselves with y-intercepts. Well, that's 0 comma something. Well, y-intercepts are exclusively when x equals 0. So if you plug 0 in for all your x's in the whole function, whatever it outputs is always going to be your y-intercept. How we're going to find that quick, short, and easy on our CAS calculator is we're going to say Menu, Trace, Graph Trace, and then we're going to enter the number 0. And what it's going to do is it's going to go straight to when x equals 0 on the graph, and it's going to plot a point for us right on the y-axis, okay? And from there, we are going to drag down here. We're going to look at symmetry as well. And symmetry, if you remember, you probably haven't talked about symmetry since algebra. You probably talked a little bit pre-calc about it. But symmetry, there's actually two types of symmetry. You either have y-axis symmetry or origin symmetry. It's either y-axis, origin, or you do not have symmetry. Symmetry is a nice thing to identify later in the year in calculus, because when we hit integration, it's going to help you shortcut to evaluate integrals. What is y-axis symmetry? Well, what y-axis symmetry is on a graph, if I have the point xy, and then I put the opposite of x in, it's going to output the same exact y that I had before. Okay, that would be an even function. The most common example of an even function would be the graph of y equals x squared. Okay, just the parent graph of that. And the reason why it's important is when I put 0 in for y, I get 0 out. If I put 1 in for x, if I put 0 in for x, I get 0 for y. If I put 1 in for x, I get 1 out for y. Conversely, if I put -1 in, I get 1 for y. So if I put the opposite in, I get the same y output out. If I put 2 in for x, I get 1, 2, 3, y. And if I put -2 in, I get -4 out for y. And I can see that this dirty dog has really nice y-axis symmetry. If I envision a line cutting just straight down the y-axis, I am perfectly symmetrical on both the right side and the left side. That is graphically identifying it. Well, what it means algebraically, if you remember, everybody hated this in Alg 2, that means if I took my function and I put the opposite of x in, what happened was it equaled when I put the regular x in. So basically all that's modeling is if I put f of 1 is the same as f of -1, they're equal because they're symmetrical across the y-axis. Okay, so that's the algebraic look of an even function. And I'm just going to get rid of the 1, get rid of the -1. Okay, there's another common even function, and the next one would be y equals cosine x. Everybody's favorite, some trig. Why is that an even function? Well, if you remember, if you graph the cosine function, you had your wonderful unit circle, and the cosine, we always went 1, 2, 3, 4. The cosine started at a maximum, then it went to a 0. Then this is going to be 1. I'm going to say this is -1. Then it went to its minimum, came back to a 0, ended out at its maximum, and it went like that. And because that was a periodic function, basically I could take that backwards and I could see some more spots. I'd say 1, 2, 3, 4, and I could graph another period before it backwards, and I could continue that graph. And I can also see that when I graph that whole thing, if I cut the y-axis apart, it is perfectly symmetrical. If I folded my graph on the y-axis, the left side is going to fold and go right on top of the right side. Okay, that's odd and even functions. Or that's just, excuse me, y-axis symmetry, which is an even function. Well, when we have origin symmetry, it's an odd function. Well, what does origin symmetry mean? Origin symmetry means that, well, I'll show you what it means. When I put the opposite, when I have a point x, y, if I put in the opposite of x, I get out the opposite of y. So these two ordered pairs, okay, they map directly across the origin in a manner such that if you connected those 2 points, that line would go through the origin every time. That would be an odd function. Algebraically, my odd function, okay, odd function algebraically meant that if I put the opposite of x into my function, I got out the opposite of y. And I know we hated that notation back in the day in Algebra 1. I don't remember if you did it in pre-calc. I haven't taught it at West. I did it in my old pre-calc class. But that is algebraically how we do that for an odd function. We will work more and it'll come out more and more throughout the year, so don't panic if you do not remember it all. What does it look like graphically? Well, most common, or I shouldn't say the most common, but the one I always think of is y equals x cubed. See, the beauty is if I have a polynomial function, in every power of x, all the way through it, every power of x is an odd number on that power. It's going to be an odd function with no constant. Same thing for an even function. If every power of x is even, it's going to be an even function. Okay, kind of neat. So when I'm looking here, if I did that, if I put 0 in for x, I get 0 out for y. If I put 1 in for x, I get 1 out for y. If I put 2 in for x, I'd get 8 out for y. And on the flip side, if I put -1 in, well, -1 to the third power, that gives me -1. And if I put -2 into the function, well, that's going to give me I'm going to just label that as -8. That's going to give me down here at -8. And that graph is going to kind of wiggle and squiggle, and it's going to come up. But if you notice, like I said, I should really put arrows on my graphs too. I should get technical on that. And it comes down. So if you notice, in odd function always, a mapped pair, I have a crappy graph here, but if I connected those, that line should be going through the origin, and not should be, it will be going through the origin. Therefore, it is an odd function. One other odd function that you'll work with a ton in calculus is you're going to see y equals the sine x, another trig function. People hate trig. I love it. It's got wonderful places in math. But why is that an odd function? Well, if I graphed, I want to use my red, if I graphed my sine function, if you recall, because it's a trig function, I had again 1, 2, 3, 4 points. Well, the sine started at 0, then it went up to its maximum, it came down back to its 0, it went to its minimum. Remember the amplitude, it might have stretched more higher or lower than 1 or -1, then it came back to 0, so it kind of came across like that. And if I stretched out another period backwards, 2, 3, 4, well then it came to the minimum backwards and went there, came back up, and then it came back down, so I could continue that. And then if I took any mapped pair on this sine function, okay, there were identities for this and all kinds of fun stuff. If I took this point, it mapped over to this one. If I connected them, it went through the origin. If I took this point, we know this point maps across to this point because they were opposite. It's going to map across and it goes through the origin. That is what an odd function looks like graphically, okay? So there's ways to algebraically prove odd and even. This is the mathematical proof to prove all values for x are and that are odd. This is for all even. Excuse me. But we'll be working more with that. Odd and even functions are more important later on when we hit some integration. Big part is knowing knowing the symmetry, number 1, being able to find x and y intercepts, number 2, on a graph, okay? We do not have x-axis symmetry. Well, we do have x-axis symmetry. Some graphs do, but if you do have x-axis symmetry, then it's not a function because then you're hitting 2 points, okay? What are you talking about, Kruger? Well, here's one for x-axis symmetry. One conic section, a little sideways opening parabola. Notice that little guy has x-axis symmetry, but we don't work a lot with that. We don't work with that really at all in calculus because it's not a function. It fails the vertical line test. So x-axis symmetry is not a function. We typically only talk about functions in calculus. And the next thing we're going to talk about in our quick little review session here, and I say quick, I'm going to try to keep these videos relatively as short as I possibly can. You can fast forward through them whenever you want, but we're going to talk about asymptotes. There's 2 types. There's vertical and there's horizontal. First, we'll talk about vertical asymptotes. Well, what the heck are they? Well, what I'm going to do is come on the side because we work a lot with these. Most of your asymptotes, graphs that can have both of them, are rational functions, okay? Exponential functions have asymptotes. Logarithmic functions have asymptotes. They all have them. But what the heck is a vertical asymptote? A vertical asymptote, explicitly, definition, means at x equals some value, we're just going to call it c, we have a vertical asymptote at that value when x equals c, if what happens as x approaches that c value, what happens is y approaches either positive or negative infinity. You might hear me say throughout the year, it's going asymptotic. What that means is as your graph is getting close to that value for x, we're going to call it c, the closer and closer to that value it gets, your graph is either going straight up or it's going straight down. That's what it really means, okay? It doesn't have to be. It's not necessarily both of them. It may just be one of them, okay? Horizontal asymptote, definition of a horizontal asymptote. You have a horizontal asymptote at some y, and we're going to call it b this time, if as x approaches either plus or minus infinity. Remember, these are called end behavior asymptotes when they get way out to the left or way out to the right. What happens as I get super huge x values, my graph, my y value, is going to be approaching that particular b value. Okay? Now, how did we find these? Okay? How did we find them? Algebraically, we find vertical asymptotes. They typically happen when the denominator of a rational function equals 0. Anytime the denominator of a rational function, anytime it equals 0, anytime any fraction has 0 on the bottom, it's undefined. We don't know because you can't divide by 0. Okay? How did we find horizontal asymptotes? Well, we found these once we remembered our shortcuts by comparing, okay, powers. What are you talking about? Well, in rational functions, what we did was we compared the biggest power of x in the numerator and the biggest power of y in the denominator. And what happened was, if we found the degree of the numerator, or the top, if the top power was smaller than the degree of the denominator, so if the numerator had a bigger power of x than the denominator did, we found the horizontal asymptote was always at y equals 0. And when our powers equaled, when the power in the top equaled the power of the bottom, my d just stands for degree. I'm stating it as a power because it's the power of x. It was at y equals the lead coefficient, or the coefficient on that biggest power, divided by the coefficient of the power in the denominator. And we also found that if the power in the numerator was bigger than the power of the denominator, what happened was we had none. We did not have a horizontal asymptote. Okay? Now, what I'm going to do is I'm going to give you a couple examples here. Turn this on. I'm going to grab my calculator. And what I'm going to do is I'm going to make a new document. And no, I don't want to save it. I want to make a new graph. Okay? So what I'm going to do is I'm going to graph, control divide for my fun fraction. I'm going to graph x plus 1 over x plus 2. Okay, that's a rational function because it is a polynomial divided by a polynomial. That's going to give me my graph. Now notice, what happened in there is we visually could see our asymptotes. We could visually see that there is a vertical asymptote at x equals -2. Okay, we could see it there. We could see it's got a horizontal asymptote at 1. Well, get that off of there. We can find these graphically at the same time. Horizontals are what we're going to do to find a horizontal asymptote is we're going to say menu. We are going to trace. We are going to trace the graph. And right now you see it's at 0 down here. That's my y-intercept. But if I put, it's asking me for a value, if I put like a 10,000 in, what it's doing is it's showing me an ordered pair down here. It's at 0.999. So it's getting super close to 1 from the bottom side. Approaching top, approaching bottom. So when I get way out to the right, I'm approaching that particular graph. Then what I'm going to do is I'm going to take my window back to a standard, and it brings right in. Now I can use the same thing for my vertical asymptote if I really wanted to. I could say menu, I could analyze graph. No, I want to trace it, sorry. I'm going to trace graph, and it looks like it's at -2. So if I put like -1.999, I can see at -1.999 here in the bottom right corner, my Y value is just about -1,000. So it is diving, it is plummeting, it's a vertical asymptote, which you knew because you could see it. Now I'm going to take my window back to my standard. Okay, so that's what they look like there. And we have some other crazy things that happen too. But one other example, I'm just going to get rid of my calculator. For one other example without this, what I'm going to do is I'm going to extend my page. I'm going to grab a blue one. I'm going to make, here's my X and Y axis. What I'm going to do is I'm going to say f of x. You can graph this in your calculator if you want, but I'm just going to take x squared plus 4x, and I'm going to divide that by x squared minus 9. Okay? Now, if you remember algebraically finding them, you may not, but what we're going to do is I'm going to say 1, 2, 3, 1, 2, 3. I can see in this denominator here, positive and 3 and negative 3, they're going to give me undefined, so I'm going to have vertical asymptotes there. And the thing that freaks people out when we're talking about asymptotes, I can never touch or cross a vertical asymptote. I'll never touch it, nor will I physically cross it. Horizontal asymptotes, I can. When I'm looking at this one here, I never touch that horizontal asymptote across there. But the one I'm going to do now, it really bothers people, but it's doable. I can see in the top here, if I found the zeros of my numerator, I can see I'm going to have an x-intercept at, if I factored that, I got x times x plus 4, right? So I'm going to have an x-intercept here at 0. I'm going to have an x-intercept at 1, 2, 3, -4. And if I look here, if I compare my powers, okay, notice the biggest power in the top is x squared, the biggest power in the bottom is x squared. Because those degrees or powers are equal, I got to take the coefficient on the top, which is 1, and the coefficient on the bottom, which is 1. So my horizontal asymptote is going to be at y equals 1 over 1, or 1. So what I would do is I would say, I don't want the green yet. I'm going to say here, I got a horizontal asymptote. I usually do my horizontal asymptote, all my asymptotes in red. Why? Because that's the way it was taught. And then from here, if I continued to build out a table, which I'm not going to do, what I'm going to find out is my graph looks like this. Stays on the bottom. It's going to kind of come up here. It's going to go, and as I get closer and closer to that vertical asymptote, it gets snug as a bug in a rug to the left. And as I get closer and closer to positive 3, it gets closer and closer to that. And then I can't touch that, so this one is going to be up here. And the thing a lot of people really wig out about is it is possible to touch. This is y equals 1. This is x equals 3. And x equals -3. I can touch and cross that. Doesn't mean I ever will, but if I do, it's going to be somewhere here in the middle of my domain. It's never going to be way on the outside of my domain if I do cross them. They're way to the outside, okay? So we're going to turn the page. Hopefully this is making a little bit of sense. Maybe, maybe not. And we're going to get to maximum and minimum points. Well, what the heck are those? Well, maximum and minimum points, well, that's where you change from increasing to decreasing, Okay, I have a maximum or a minimum when I change from increasing to decreasing, or a change from decreasing to increasing. I will have a maximum or a minimum there. We're going to find that in our calculator by menu, analyze graph, max or min. You got to pick which one it is. It's a maximum or a minimum. We're going to find it. Intervals of increasing and decreasing, well, they happen. This is part of the domain. Intervals of increasing and decreasing, that's part of domain. It's part of the domain where the curve is going up or going down. Okay, the going down part is decreasing, and the going up, I know you know, is the increasing. Okay. Well, let's just say, I'm not going to type these in. We're going to find all these in our calculator here in a little bit, but let me just chuck a sketch up here. So I'm going to make a sketch, and on this sketch, I'm just going to make a random curve. Looks like a cubic polynomial. And as I'm looking at this, what happens is I can see right here, I have a maximum because I had a change from coming up to going down. I have a minimum because I had a change from going down to going up. I know you knew that. So what we're going to do is we're going to call this point right here x sub 1. We're going to call this point right here x sub 2 because they're two different points. I don't know what the function is. So my max is technically happening at x1 comma y1. You got to get used to a lot of variables in calculus. And my minimum in this case is going to be at x2 comma y2. So when we're talking about intervals of increasing and decreasing, okay, what we can see is right here, because you always do this as you're reading your graph left to right there on that green, I'm increasing. Then I'm having a change from that maximum to that minimum. I have a change where my graph is going down and I decrease. And then I hit that minimum. And when I hit that minimum, I am changing to increasing. So what we do is we're going to say our intervals, my interval of increasing, this is where we had our interval notation. I'm increasing, I don't know what any of these things are, but I do know way out here is negative infinity for x, and out here it's positive infinity for x. Intervals always have to be given in terms of x values because x, when I think of a function, just remember, functions are denounced by f of x equaling something. X is the boss. X controls what y is going to be. So if I'm looking here, I can see here I'm increasing beginning at negative infinity all the way out on the left, all the way up to this point right here would be x sub 1. And then I decrease. Well, when am I decreasing? Well, right there at that x sub 1, that's when I start to fall all the way down to x sub 2. And then union at that x sub 2, whoa, come on, at that x sub 2, get the right one in there, x sub 2, what happens is I increase forever and ever and ever, or until infinity, it never stops, okay? Typically, if you remember, interval notation, we can use parentheses, which do not include the endpoint, and we used brackets that do include the endpoints. And a lot of it's, if we were in person, somebody would have brought that up and somebody has said, well, do I use open brackets or closed brackets? And basically in calculus, when you were talking about intervals of increasing and decreasing, it really does not matter, okay? Unless if this point right here, if that x value is not in the domain, meaning if that's an open hole, then I could not use a bracket. Otherwise, if you always use parentheses, you're fine. Never, ever, ever put a bracket on infinity because that doesn't include it, because infinity means never stop, basically, okay? The only time, if you basically always use parentheses on increasing and decreasing intervals, you will always get them right as long as you have the appropriate numbers inside there, okay? We're going to turn here. We have points of inflection. Probably didn't talk about these guys last year in pre-calc, but that's okay. We'll go over them. Points of inflection, no, those happen when I have a change from concave up to concave down. Concave up to concave down, or vice versa. Doesn't matter. If I have a change from concave down to concave up, I have a point of inflection. I know in Algebra 2 we do identify these. They are very special points in calculus. They will be points at which when we talk about acceleration and velocity and position, inflection points are points at which your acceleration is zero, okay? Concave up and concave down intervals. Well, if you're forgetting, parabola, concave up because it can hold water, it fills up. Concave down is like the mountain, okay? Concave up, concave down, okay? Concave up and concave down. Concavity is how the curve increases or decreases, okay? How the curve, concavity talks about how the curve increases or decreases. What the heck are you talking about? I'm going to tell you here in a minute. It's on our next page. Before I hit that, I just want to model how to do an interval of concavity. So what I'm going to do is I'm just going to make another little graph. I'm just going to make an x-axis. We don't really care where the y-axis is. And I'm just going to make another kind of polynomial sketch. And I'm just going to make it a cute little guy there. Okay, got a few changes in there. Okay, now as I'm looking at this, I can see, whoa, I have a minimum, which doesn't matter. I have a maximum. I have another minimum. We will talk later on about local maxes and mins and absolute maxes and mins. These are all local because they are not, they're talking about in a general vicinity. If it was the absolutely highest or lowest point in the graph, like this one appears to be an absolute. It appears that I drew that the absolutely lowest point of the graph. That would be absolute. These two would be relative, or some people call them local. But when I'm saying concave up or concave down, when I have a change in concavity, what I'm doing is as I am following this curve up from this minimum, I can see I'm going up, up. I can see it's going to hold water. And somewhere in there, all of a sudden now it changes into a mountain. Somewhere in here, I changed from concave up to concave down. And then back to concave up. Okay? And I could probably say CD and CU, but I usually do conc and then use up or down. So somewhere right in there, and it's a It's a judgment call. Our calculator is going to find it perfectly, but it's a judgment call where you think, and you can put a little star there, not a point. It looks like, I'm going to call this one x sub 1 because it's furthest to the left. And it looks like somewhere in this general vicinity, I'm going to have another change, and I'm going to call that little guy x sub 2. Okay? We're not going to be algebraically finding these right now. We're going to be finding all of these with your calculator in a bit. So if I did my intervals of concave up and concave down, what I'm going to do is I'm going to say, remember, negative infinities way to the left, infinities to the right, and I'm going to say concave up, and I'm going to say concave down, and somewhere between that maximum and minimum, typically, and I'm going to say typically, we have a point of inflection. And I'm going to say not always, and nobody's here to ask me the question, well, when wouldn't you have one? We're going to have quite a few examples when they don't have one, okay? But if I'm looking at concave up, I can see I'm up, concave up, beginning at negative infinity, all the way up to this point right there, x sub 1, and then when I get to the right side of x sub 1, now I'm concave down. So I'm concave down from x sub 1, and I'm down right to that next point of inflection at x sub 2. And as soon as I get to the right side of that x sub 2, check it out, it's concave up. So I'm in union with x sub 2 out to positive infinity or until the end. Somebody was here saying, do I have to put that U for union in there? Yes, you do. If I don't put it in there, is it wrong? Yes, it is, because it's talking about two. This graph is concave up both of these times in that union. And if you don't put them as a union with a comma or something, they're just straight up not right. Okay, so points of inflection are when I have a change from concave up to concave down. Points where concavity changes as a point of inflection. Like I said before, when we talk about acceleration, velocity, and position, acceleration, we're going to find out is the second derivative of a function, and that is when your acceleration is 0 at a point of inflection, because it's talking about how steep this curve is going up. It's going up, it's increasing, and it's still increasing, but there's a change right at that point, how it's increasing. What the heck are you talking about? Well, what I'm talking about is on our next page here, we're going to sketch 4 things here, and we're going to classify it as concave up, concave down, or no concavity. Okay, well, so what we're going to talk about is if I'm increasing at a constant rate. Okay, remember, increasing means as you're reading a graph, you're going from left to right, your graph goes up at a constant rate. That would just kind of be a line. And lines have no concavity. Okay, if I'm decreasing, or excuse me, if I'm increasing at a decreasing rate, what does that mean? Well, that means my curve, yes, curves are going to have slope, we're going to find out. I'm increasing at a decreasing rate. So as I'm reading left to right, my curve is getting flatter. However, if it's going up, if it's increasing from left to right, my curve has to be going up, and then my curve starts to curve like that. So if I actually saw tangent lines on this, the slope of each one of these tangent lines we'll talk about, the slope of those tangent lines are decreasing the further along that curve I get. Okay, so this would be if I'm increasing at a decreasing rate, I am concave down. If I'm increasing at an increasing rate, I'm going up and my tangent lines are going to be getting steeper. What does that look like? A little something like that. picture your tangent lines. Your tangent lines are getting steeper and steeper. So if my graph is increasing at an increasing rate, I'm concave up. Okay? Well, how about what happens on a decreasing curve? Well, what happens if I'm decreasing at a constant rate? Well, left to right, that means I'm going down, doesn't it? Well, no concavity. I need a curve to have concavity. Lines don't have curve, or lines don't have concavity, curves have concavity. If I'm decreasing, meaning left to right, I'm going down at a decreasing rate, meaning my tangent lines are getting flatter and flatter as I'm picturing, like on B, my tangent lines of those red ones are getting flatter and flatter. If I'm decreasing at a decreasing rate, so left to right, curve is going down, left to right, tangent lines have less slope. That means I'm concave up. What I mean by that means I'm concave up. If I have something that's decreasing at a decreasing rate, I know the graph is going to be concave up at that point. Okay? And if I'm decreasing at an increasing rate, what would that look like? Well, left to right, my curve's going down, but my lines are getting steeper. Just like that. Okay? Left to right, it's going down here, but I can see my tangent lines, the slope of them are increasing. So if I'm decreasing, if I have a function that's decreasing at an increasing rate, it will be concave down at that part of its graph. Okay? Now, what we're going to do, actually we're not going to do that yet. We're going to talk about domain and range. Okay? You know what domain is? It's all the x values. I don't have to write that because I already had it written. Range is y values for the graph. Here, when you're talking domain and range, must use parentheses and brackets correctly. Okay, you have to use them correctly there. All right, so what I'm going to do is we're going to come back here quick and I'm going to grab my graph, graphing calculator. I'm going to put a new graph on here. I'm going to control, divide, and I'm going to do example. The example that's on there, which is 3 minus 4x over x squared plus 1. Okay? Wicked looking graph. Okay? We're going to look at this graph and we are going to be able to find out x-intercepts, y-intercepts, and all that good hunky-dory stuff. Except it's important you can just do it with your calculator as well. So if I wanted to find the y-intercept, I'm going to say menu. I'm going to say trace, trace graph. And then I'm going to put a 0 in for x, hit enter. And if I hit enter again, it's going to drop my y-intercept. Okay? If I need x-intercepts, I'm going to say menu, analyze graph. We want zeros. Now we can see where it crosses the x-axis and we got to take our finger on that little touchpad and we need to make sure we're first on the lower bound or the left side of that intercept, anywhere on the left side, and then drag it to the right side and it automatically drops the dot. Okay? And then you can move these little guys around. And then because these, I should have come in here and I should say menu, and I should say, when you're in a graph page, we have to go to settings as well, and also make sure in your graphs and geometry settings here when you're in a graph, make sure you're also on float, because we have to accurately round to 3 decimal places and then make that your default. Okay, and it's going to show you a whole bunch of decimals for each spot. As you're looking at this stuff, I'm going to just move these things around a little bit. So what I would do to answer my homework questions is I would be looking here and I'd say my y-intercept, yep, that was 0, 3. Well, I could also put a 0 in here, a 0 in here. See, it's going to equal 3 over 1. Oh, when I put a 0 in for x, I get 3 out. Woo! That's how you algebraically find them. You knew that. When I'm looking for x-intercepts, the calculator found it really quick for us. It was at 3/4, or 0.75 for the decimal freaks, comma, 0. Well, how do we do that? Well, in a rational function, if you take the numerator expression, 3 minus 4x, set it equal to 0, and solve it, like if I add my 4x across, I get 3 equals 4x. You solve for x, x equals 3/4. That means if I put 3/4 in here, it outputs 0 for y. So that's how you algebraically find your x-intercept. Set the numerator equal to 0. Okay, we found that. Well, symmetry. Is there any symmetry to this thing? If I divide it across the y-axis, it's not symmetrical. If I looked at this point, like if I went and I traced the point, trace graph, if I put a 1 in there, I'm right down here, you can see where that target is. Trace where -1 is. If you put -1 in and connected those dots, is that going to go through the origin? The answer is no, does not have origin symmetry. Okay, so none. I'd write none. Vertical asymptote, I think that was pretty apparent that there was none of those. Also, because it's a rational expression, if I took this, is there any way x squared plus 1 will ever equal 0? Well, x squared will equal -1. And some people are going to say, well, yeah, we can do that because x would actually equal the imaginary I, but we're not in the imaginary coordinate plane. We're talking about real numbers. We won't be working with imaginary numbers in this class. There's a whole separate calculus class, calculus for imaginary numbers. We're not dealing with those. Horizontal asymptotes. Well, let's come back here to my graph. They're easier to find. Well, if I want to find it in my graph, what I'm going to do is I'm going to say menu, trace, we're going to trace the graph, and we're going to put like 10,000 in there, really big number, and I can see in the bottom right corner, it's giving me that 10,000 comma 0.0004, -0.00. That's pretty small. It's pretty close to 0. Looks like it's getting closer and closer and closer to the point if I put 100,000 in there. Oh, it's getting smaller. Looks like y equals 0 is my horizontal asymptote. Come back to my Windows Standard, and I don't need to worry about it. And horizontal asymptote, y equals 0. Also, remember I said the powers. Well, here's the big shooter in the numerator. Here's the big shooter in the denominator. Well, what is the degree of the top? I have degree 1, and I have degree 2 in the denominator. Okay, so this is my degree of numerator is less than degree of denominator. And if you go back to the first page where I talked about that, what happens is y equals 0 will always unconditionally be the horizontal asymptote when that power relationship happens. And there's specific reasons why. And we'll talk about it when we hit infinite limits, okay? Right now, just want you to remember that stuff. Maximums and minimums. Hey, our calculator finds those really nice too. So I'm going to come back. I can see I have a maximum here. Ooh, it looks like an absolute maximum. How do I find that? Well, I go menu, analyze graph, maximum, And then I have to make sure, drag my finger across that pad. It says lower bound. That just means the left side of the hump. Drag it to the right side of the hump, and it drops the dot for me. And I can drag it up. So there's my maximum. If I want the minimum, I can go, actually, let me show you something even cooler. Let me come back here. Let me get rid of these points. Let me give that point, let me delete it. Let me give this point, let me delete it. This usually works, hopefully it works for me now. Okay, so if I go menu, trace, trace graph. As I toggle, whoop, check it out, it said y-intercept. If I hit enter, it'll drop it. If I toggle to the left, ooh, it missed it. Didn't get it for some dumb reason. Oh, there's my 0. I can hit that. If I keep going across, minimum, as soon as it usually will stop on both of them. And for some reason, this dirty, rotten scoundrel is not grabbing that. So I would exit out of that. And in that case, when I can see I'm missing it, then I would do my analyze graph maximum and have it drop the dot. Typically, when you use a trace, it's going to stop on your y-axis. It's typically going to stop on all of your x-intercepts, and it's going to stop at your minimums as well. But notice it didn't stop on my point of inflection. Well, so I'm going to come back here real quick, and I'm going to fill those in there quick. So my maximum, we said, was negative 0.5 for the decimal freaks 4. Or that was my maximum, excuse me. Minimum was 2 comma negative 1. So I can see when I'm increasing and decreasing, I increase and decrease between here. So negative infinity is way over here. I'm increasing to that maximum. Then I decrease to the minimum. Then I increase again. So what that means is when I'm writing my intervals, I apologize for the length of this video. I'm going to hone in better on them. What that means is I'm going to increase from negative infinity all the way up to negative 0.5. And then I decreased from negative 0.5, and I usually do these in conjunction across. And after I decreased, I started increasing again from 2, notice, out to infinity, but I went negative infinity to a half, and then I was at from a half to 2, and then I went from 2 to the infinity. So I kind of track these all the way across. The infinity, there's my half to 2, 2 out to infinity, and they kind of come across like that. Points of inflection, concave up, concave down. Well, check that out though. I'm increasing, concave up, okay? I'm increasing, concave down. I can see concave up, concave down, concave down, concave up. And because this side doesn't continue to go up, it has to change and go concave down again. So what we're going to do is we're going to go find those inflection points. I'm going to say menu. We're going to say analyze the graph. We want our inflection point. Now, so anywhere, I know I'm concave up here, and I'm going to drag it until it drops. Oh, there it is. There I had a change, concave down. There's a point of inflection. Then, because I knew there was more, I'm going to say menu, analyze, inflection. I'm going to go from that point of inflection where I'm concave down. I'm going to drag it. Oh, there's another one. And I'm going to grab that little feller here. They're ugly decimals. Then I said we looked like we had another one. We're going to analyze that graph one more time. For inflection, I'm going to go from that point of inflection to, oh, there's another one. And then I'm just going to move that one down there. In your graph, you just got to track. You can move those numbers around where they need to be. And the reason why we need the float decimal is, remember, we want 3 decimal places, okay? So when we write our answers in calculus, we're going to say negative 1.0. Ooh, are we? Yep. 99. Is that x? And over here, we got to look at that. So that's going to be 0.218. And then here, whoop, that's going to make me round that up 3.132 when I'm writing those intervals, okay? And I take a screenshot, but you have those on your calculator, hopefully, to where when I come back here, I can write my inflection points down, the whole point. I have inflection points at negative 1.099, comma 3.349. And because these are points, not intervals, I don't use the unions. I use commas, 0.218, comma 2.032, comma, and I had a third one, 3.132, negative 0.882. Then when I went concave up, easiest way to look at it, when you're looking at your graph, you're up, then you're down, and then you're up, then you're down again. So I should have 2 intervals for up, and I should have 2 intervals for down. And the way I listed my points, I can come right back and I can lay those little bad boys out here. Now, concave up, where was I? I started, come on baby, I started at negative infinity until negative 1.099. And then I was also, usually I'd go from negative 1.099 until 0.218. And then at that 0.218, I went up until 3.132, and then union with 3.132. Forever and on, I was concave down. Okay? When I'm looking at the graph, does it look like there are any holes, or are there any vertical asymptotes, holes, anything in that graph? Looks like it goes on and on and on forever, doesn't it? Therefore, my domain is all real numbers, double-legged R. Or you could say negative infinity to infinity. Easiest way, I like that. The range covers all the x's. It started the left one all the way to the right. The range, though, the range didn't look like it went everywhere, did it? Whoa. Whoa. Come on. Whoa, wrong one. Come on. Big dummy. There, we got it. The range, it only took y's from that maximum. Now, because I'm talking range, I got to talk about y values. The highest point it gets is 4. And because this was my minimum, the lowest point it gets is negative 1. And because my calculator dropped those dots, it's including those points. My range would go from, whoa, come on, negative 1 to 4. They have to be brackets because it includes those points. And then from there, I'm going to leave it open. I do more examples. I don't want to do more examples. I already took way too long on this video. So office hours, hit me up. Have a good day.